welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Melisa Orta Martinez, who is an assistant professor in the Robotics Institute at Carnegie Mellon University. And there she leads the Social Haptics, Robotics, and Education Laboratory, which is a nice acronym, which is SHRED. So something about Melisa. She received a PhD at Stanford, and her research combines the areas of robotics, haptics, human-computer interaction, and quite uniquely also education. So she develops robots and engineering solutions for communities. If you have seen her work, she's been working on a variety of projects that include low-cost open source robotics, technologies that also have sometimes an educational purpose. So I found this very, very interesting. Analyzing, she's also works a lot on analyzing the interface between technology and learning, for instance, studying the sense of touch and developing new mechanisms for human-machine interaction. Today, Melisa will talk about we give a talk titled From Haptic Devices to Interactive Machines, Unlocking the Power of Our Touch Sense. This is exciting work. I've been following some of the papers, but I'm really happy to hear more. Feel free to ask questions in the chat during the talk, and we'll monitor and try to answer them. But without further ado, Melisa, thank you again for coming, and the stage is yours.
No, thank you so much for the introduction, Jill, and thank you so much for having me. Yes, so as Jill very nicely put it, my work combines the areas of haptics, robotics, and education. And today I want to talk about some work in the areas of haptics and education and how to combine them. This work is pretty new. A lot of it's unpublished. So yeah, but I'm happy to answer all of the questions. I think in order to get started, what I first want to do is introduce the sense of touch a little bit. And so I want to do an exercise. I know everybody has like their cameras off, but if you can humor me, if you're not looking at yourself, you can like point your fingers and stretch your arms out and then touch your fingers up above your head without looking, right? And so if you do that, right, and you see that you can do that, that is all thanks to our amazingly powerful sense of touch. And I think this is an activity that really highlights just how powerful it is, because when we think about touch, a lot of the times we think about like things that we sense through our skin, right? And that's more so our cutaneous sense. So things like temperature and texture and slip and moisture, and that's all our cutaneous sense. But we don't think about a lot of is that our sense of touch also gives us our sense of proprioception, which is where my limbs are in space. And we can do a lot of things really without thinking about it, thanks to our sense of touch. And so, for example, when I was pointing my hands out and extending my arms and then touching them, I don't really need to look or think about where they are because I always know, thanks to the fact that I have sensors in my skin that when my skin stretch, they tell my brain, hey, your skin's stretching. Sensors in my muscles that also give me information where they are in space, sensors in my joints that do the same thing. And so thanks to all of that, I can move around and I can walk around without really having to think about it, right? And so that's why for me, it's very interesting to look at our sense of touch with education because we do a lot of things kind of automatically and by intuition through our sense of touch. And so it's can we bring these same activities to having more, how do you say, more intuition about things in the educational space. And I will talk more about this and I will explain more. But then to get started, I also want to give an example of a popular haptic device. So also we get into the framework of what we're talking about when we're thinking about like using our sense of touch and kind of building robots and devices for them, which is what we do a lot in my lab. And so this device right here, this is not from my lab. This is from a computer called 3D Systems. It's called the Touch. And so what I want to explain is this is something called a kinesthetic haptic device. And so what it does, it's basically a little robot arm. And what you do is you grab into the end effector of it, and then you can feel virtual environments through it. The way those virtual environments feel, it's the way they feel is as if you were like holding a pen and touching something with a pen. So when you're touching these virtual custard dessert, you're gonna feel forces that are rendered through this little robot. And so you'll feel like the stiffness of the virtual environment, for example. You're not gonna feel directly like the moisture or what it would feel like if you were like to touch it with your finger, right? But you still feel like you still get a lot of the sense of touch through it. So that's kinesthetically, like that's a device that's rendering forces to us. Now, of course, our sense of touch is incredibly complicated. We have a lot more sensors than just to sense forces, right? So when you touch something, you feel its texture, you feel its moisture. That's because we have hundreds of receptors all over, actually thousands of receptors all over our skin that give us a lot of information. Now, the way these receptors behave is they all kind of respond to different frequencies. You can think about them as little bandpass filters. And so different sensors will be sensitive to different signals, different kind of like force, pushes, pressures, strains, and different frequencies. And so the thing about the sense of touch, part of the research that goes into it right now is just trying to understand it. Because even though we understand like, oh, we have all of these different types of receptors and they're kind of responding to different frequencies of how you get pushed basically on what you're touching, we don't quite understand the relationship between that and exactly why it is that we feel what we feel. And so to illustrate that, let me give an example from the sense of sight. So for example, in the sense of sight, I would say that we understand it pretty well. And I know there's still like ongoing research, like of course we don't understand everything about it, but we understand it pretty well. As in like, we understand that in our eyes, we have different types of cones. Those cones are gonna sense different frequencies of light, right? And we understand what those frequencies are. We understand that we sense light at frequencies of red, green, and blue. And we understand how they get combined together to give us the images that we see. Now, because of that, so if I'm looking at my dog, for example, I can take a picture of my dog and then I can decompose that picture into its principal components, right? Which is basically just a weighted average of those principal components of red, green, and blue. And now I can feed that to a computer as numbers. And because of that, now a computer can recreate that image that I took, right? In my brain, my mind, and I can process it too. And that's why the field of, things having to do with vision has exploded, right? We have computer vision, we have like self-driving cars, processing images, graphics, etc., etc. It's because we understand pretty well how to break down what we're experiencing as numbers. Now, in the sense of touch, if instead of just looking at my dog, I'm now touching my dog, right? What would I say about what it feels like? I will say something like, well, feels fuzzy. But then that transformation, like, what does that exactly mean? Like, what does fuzzy mean? How do I decompose fuzzy? That's what we don't quite understand yet. And so, as I said, we know we have all these different receptors, right? We know that they have an incredible amount of resolution, and there's theories of like, oh, actually, there should be some sort of dimension, like a principal component should be, for example, friction, right? Principal component should be texture. These are just theories. And a lot of people are working on, proving these theories and understanding what the actual dimensions are. Now, the thing about understanding these dimensions and proving them is that it's kind of like a chicken and egg problem, where the actual mechanoreceptors that we have it's so complicated. They have such an immense amount of resolution. Like some of them, for example, have a resolution of 0.5 millimeters, right? And they have a bandwidth, like some of them have bandwidth up to 1,000 hertz. And so in order to make an actuator that where we would be like, oh, okay, I want to be able to recreate everything that I could possibly sense in the environment, you would have to have an actuator that's like 6 degrees of freedom with a resolution of 0.5 millimeters. You would have to have hundreds of them packed together so that you could actually kind of like recreate everything that we feel in order to understand it, right? And so let me give an example of one of my favorite tactile haptic devices. This is a device, again, it's not from my lab, that's just interacting with your skin. I don't know why it's not playing. Wait, let me see. Why the video won't play. All right. Video is not playing. I will play it manually. This is a device from Stanford University from Alison Okamura's lab, and it's one of my favorite tactile haptic devices because it's an amazing 3-degree of freedom pantograph mechanism. It has this little ball, this little like end effector here that can dig into your skin, and it can also so give you normal forces, but it can also stretch your skin, right? And so that the reason for the purpose of this device is to study skin stretch in particular. Now, skin stretch is very interesting because when we're grabbing onto an object, our bodies are incredibly lazy. They don't want to put in more force than you have to grab an object. And so I will always hold things in a kind of near slip condition. I'm never gonna go hold an object, just carry it around, going like just grabbing it as hard as I can, right? Like this is so inefficient. And the way my body estimates how much force to put in, a lot of it comes from how my skin is stretching when I'm holding it. And so stretching your skin gives you some sort of weight perception. And so what they did with this amazing device was they made a simulation in which you carry different blocks, and then they stretch your skin as you're carrying their blocks, and then they make those objects feel different weights, right? And so it's an amazing device, totally awesome. But what I want to highlight here is that this is just interacting with one of our modalities of touch. We have one point of contact for this device, right? And in reality, we have thousands of these receptors in our fingertips. And so this is just interacting with one point, right? And all of that, right? So for just one point, it's 3 motors, it's a whole robot just for one point. And so imagine trying to recreate now thousands of these robots that should be acting at the same time to be able to actually render the signals that we feel. And so that's why doing research in the sense of touch is really complicated, because our sense of touch is very, very complicated. And so part of the work that we do in my lab is try to come up with novel materials and actuation methods to be able to do haptic signals in a novel way. And so one of the projects that I wanted to highlight is this project with my student Sarah, where we're working with partners in chemical engineering, and then we created a novel called polymer embedded with magnetic particles that is very responsive to magnetic fields. And so what we created essentially is a very soft magnet that can both be attracted and repulsed, that can do multi-point actuation. And then we tested it against, so doing, using magnetic force is kind of inefficient because, the force doesn't get transmitted so well. And so by tailoring the chemistry of this material, we were able to get on the order between 8 and 15 orders of magnitude more force transfer than the normal EcoFlex that is used normally for soft robotics. And so what we're doing with this material is creating a device where we render different textures to try and understand texture perception better. So with these devices, like what is it, like how much people can distinguish between different shapes, different spacings, etc. of these textures, and then compare them to physical textures and how much difference there is to understand kind of like, based on what this device can do, what is it that we're actually sensing where we're sensing texture perception. So that's just one example. So that's one of the things I'm very interested in, trying to develop new haptic actuation technology. Now, the thing is that even though we don't know everything about the sense of touch, right? There's still a ton that we don't know. There is a lot that we can do, and a lot of applications that benefit from us doing things with the sense of touch. And so here I have some highlighted that have greatly benefited from different tactile technology. So for example, in medical training, people look into how to do haptic simulators, so you can start your training in simulation, not have to go directly to working on human bodies. Things in surgery, for example, it is very useful since surgeons learn a lot through their hands and how things feel in order to make decisions. So when you're working now on telesurgery and operating on a patient through a robot, then trying to give the doctor the sense of touch back is very, very useful. Also in rehabilitation, to try to guide people. In gaming, we of course know that we have haptics in our games, and even in car safety, right? And so then, as we mentioned before, the application that really, really interests me and motivates me is trying to see and understand touch in education. The reason for this is that when we're babies and developing, we use the sense of touch for everything, right? There's a lot of evidence in young children that use the sense of touch to grow and learn. But then at some point, we decided that this should be our educational model, thus losing anything that had to do with the sense of touch in how we learn nowadays. However, there's a ton of evidence that shows that the sense of touch is useful even beyond those early years, right? It is true that a baby's first experience with the surrounding environment happens through touch, but there's also a lot of evidence that things like affectionate, positive touch are associated with enhanced learning and language processing, improved problem solving, and even increased physical recovery in children and also adults. Then there's also a lot of evidence showing that using the fingers to play instruments is known to build connections in the brain, which enhance mathematics reasoning. There's a lot of evidence, and to me, it's pretty clear that we should investigate how we learn through touch and what we could learn through touch, right? It might not be useful for everything, and that's fair. And the connection between touch and teaching physics, I think it's pretty well known, right? We sense forces, we teach forces. So I thought about, well, what about abstract things that don't actually exist? Specifically, trying to create concrete representations of mathematics. And so I focused on mathematics because I think we can all agree that math is one of those subjects that's really a gateway into what you're going to study, right? I think that there's a lot of trouble in how we teach math and what we believe about math. Specifically, I think that there's people out there who really do believe that math is kind of like an innate ability and that you're either born with the math gene or you're not born with the math gene. And based on whether you believe that you're born being good at math or not born being good at math, people really make career choices and lifestyle choices just based on that, right? And so it would be great if we could open up this space so that everybody could make any choice they wanted, not based on whether they believe that they're good or not good at math, right? And so now I know that a lot of you guys probably are engineers if you're coming from MIT, and a lot of you probably very good students and did very well in math. And so I don't want to take any of your accomplishments away at all, but let me reframe them a little bit. And so in order to reframe how we think about learning, let me use one educational theory called constructivism. And so I'm going to run through this pretty quickly, but basically what modern constructivist researchers have come to the conclusion is that, number one, a child will actively construct their worldview. That you can't think about something without thinking about someone thinking about something, and that concreteness actually is not a property of an object, but rather a property of a person's relationship to that object. And so if we sign on to this constructivist theory, what that means is that concepts that were very abstract at some point can become concrete for us if we kind of get into the right relationship with them. And so the more connections we have to an object, the more concrete it is to us, right? And so now having an object that's abstract and it's hard for us to understand and operate on can become concrete if we have enough representations and the right relationship with that object. And so then how could we apply these to math, which is a very abstract subject, right? And so I want to give an example in fractions, because that's another one of the subjects that's been shown for kids to be very, very hard. And so normally, or at least the way I learned math, was you didn't really learn fractions. You learned how to operate on the fractions, right? You were taught rules. For example, if you want to add two fractions together, you find the common denominator, right? If you want to divide fractions, you invert and then you multiply. And then you do a lot of these exercises, just you repeat, and at some point it just clicks together, right? Where a constructivist would say, well, that was just a happy accident. And so a constructivist, the way they would teach these is they would give you multiple representations of fractions, things that are sensory, things like pies, blocks, clocks, and also non-sensory representations, things like ratios, equivalence classes, binary reflections. And then they would give students the opportunity to interact with all of these representations, and then for them to come up with their own rules on how to operate on them. Okay, and so as engineers and roboticists, okay, why do we care about these? Like, where can we go from these? And so if we do believe that any abstract object could become concrete, if we give novel representations of them and opportunities for people to play with the concepts and develop new relationships with them, then for us as engineers, what's very interesting is how can we create engineered systems or robots in order to help people concretize these concepts, right? And this is, of course, not a novel idea. Actually, one of the first proponents of constructivism, Seymour Papert, pioneered work using something called Turtlebot, and where he made this robot to teach people how or kids how to code, and he created principles around how to do educational robotics, things like, oh, it should be open so that you can see the components interacting and you can learn more about it and you can make connections between different concepts. And that's the other thing that's very important, creating connections between not just the thing that you're learning, but the thing that you're learning with other things that you might relate to better, right? And ever since his very pioneering work, then the field had kind of exploded, and there's tons of educational robots out there, right? Now, the thing that I will point out is that most of these robots, even they give you different levels of interaction with them, right? Like some allow you to like modify them and learn mechanical design through them. Some, like this one, the Hero one, allowed you to actually change the electronics of it and build it. They're all kind of teaching you robotics through robots, right? They teach you like programming and stuff. And so they are giving you critical thinking skills that you can later bring to math, but they're not quite teaching you math directly. And that's what I'm really interested in. So how can we use these to teach math and to give new representations of math? And so in order to think about math, let's think about how we learn math today, especially once we get to like higher math, right? And what kinds of representations do we have today? And so when we learn math today, for example, when we start getting into algebra and functions, we start learning equations, right? And then in order to try and get some intuition about what this equation means or what it looks like, we do tables, right? And then we graph them. And then, the teacher's like, well, obviously. And it's really hard. I mean, it's really hard to get intuition from that. So, oh, yeah, obviously that's the way it would look like, right? And so what I want to think about is, okay, can we create tactile representations that might give us intuition and might help us understand how the equation relates to its graph, right? There are other folks, obviously, using other tactile representations. I think we've all played with tangible tiles when we were younger, and there are researchers looking at how to now express higher math like calculus and stuff using these tangible tiles. But for us, let's think about how we can do these things through haptic interfaces, right? So if we look at a very simple haptic device, right? This is a kinesthetic haptic device. It's a little joystick type thing. And so you will hold on to the handle, move it back and forth. As you're moving it back and forth, there's a motor here that you move as well. And the motor has an encoder. And so basically through kinematics, if you read how much the motor has moved, you can understand how much the user has moved the handle, right? And then inversely, you control how much torque the motor should output, right? Which again gets transformed through kinematics to forces that we feel at the handle, right? And so if I want to make this device, the user feel like something, I just need to program what is the force output that I will give to the user based on the input position that it's giving. And so, for example, if I want to make this device feel like a spring, then I will say, okay, so then the force that the user will feel would just be proportional to the position. And that makes sense. And then it will act like a spring. So as I said, that's why there's a very like natural relationship between haptic devices and teaching physics, right? Here's an example of that. So you can see it be acting as a spring. This is from the University of British Columbia, where they have this little paddle that I showed, and it's programmed like a spring. And so then they have a lesson on spring. It totally makes sense. It's like, okay, so you can change the constant. You can feel what that means in terms of like how the spring behaves, right? If you make it like bigger constant or smaller constant, you can add springs in series and in parallel and see what that does. So it's a very amazing lesson. And so, but for us, we're here to talk about math. And so let's think about how now we could create, using these same principles, how could we create representations, like haptic representations of math concepts, right? And so this here is a work that we did where we create a simulation of trigonometric functions. So same thing, same device. And so what you can do in these little GUI is you can drag and drop different trigonometric functions. And then what you feel as you're exploring it, you see this purple graph. So now the force that you feel will be proportional to the amplitude in that graph. And so you can feel the function. And then you can also change the amplitude and feel how that changes what you're feeling. And you can also change the frequency and feel how that changes the feeling, right? And so what we did is we went to a high school and we did an experiment, or like friend with kids, in which this purple graph that you see here, it wasn't shown to them. So they could see the unit circle changing, and they could see how they would explain this unit circle, but they didn't actually see the purple. They didn't see the purple line, which it's drawn here, because otherwise the presentation would be kind of useless. There's no way for you to imagine it. And then what we did is we asked them to explain to us, right? Like, if, for example, like if you change the frequency of a cosine, what does that mean for the cosine? Like, for example, if you double it, like how does the graph actually change? And they never saw the graph, they just felt the graph. And then we asked them to draw, right, the different concepts and explain to us. And what was really surprising is those students that were able to kind of like relate to the forces, they were able to do these tasks. And so these are some example drawings that they made, where they were able to be like, oh, double the frequency means this much, or raising the amplitude means this in terms of the graph. And so here, what the haptic device is doing is creating an actual representation of what it means to change one of the concepts, right? One of the properties of that function, right? There's a clear relationship between the haptic feedback and amplitude changes, and there's a clear relationship between the haptic feedback and frequency changes. And so in this case, we're using the haptic feedback, the changes in haptic feedback, to make that connection for students and get intuition as to what exactly does it mean to change those things, right? Now I want to show another example. This is newer work in which we're like, okay, so another type of functions that create trouble for students are actual polynomials, right? Especially when you get into higher orders of polynomials, for students to get intuition as to what comparing two equations of two polynomials, for example, and how they might be different from each other is quite complicated. And part of it comes from like the types of properties that we extract when we're learning math out of those polynomials. And so, for example, here, this is a quadratic polynomial, right? And so the types of things that you will learn when you're in school will be like, okay, so like, for example, like deriving the vertex and the axis of symmetry, right? And so usually the way you learn these things is you will, if you have a form, like a factorized form of the equation like this one, they teach you, okay, you should get into that factorized form, because then it's very easy to get at the vertex and the axis of symmetry, right? And if you have a more generalized form of the equation, they teach you either or and how to get into that factorized form using algebra, or they teach you new formulas on how to get those properties. But I would argue that the properties that are taught, like just getting the vertex and the axis of symmetry, do very little to give you actual intuition for you to really understand what the polynomial is, what changing different terms of it might do, how to compare it to other polynomials. And these are all very useful skills, because polynomials are actually everywhere in our life. One very useful example is we use polynomials a lot in to analyze data, right? Like if we just have scatters of data and data points, well, a lot of the times, in order to understand what is actually happening to that data and to make decisions based on that data, we use polynomials. So having intuition into, being able to compare two of these things, right, without having to do a lot of operations, it's very useful. And once you do operations on them, being able to intuitively see like, oh, did I do it right based on the results that I got, right, is also very useful. And so what we did is, okay, so if you break a polynomial up into its different terms, right, what would be very useful is for students to really understand, like in a quadratic polynomial, for example, what would be the result of changing the quadratic term, right? Or what would be the result of changing the linear term or the constant? Like, what would that actually do? And so what we thought is, okay, what if we had some sort of virtual clay that students could mold virtually? And then what we can do then is we could control how that clay behaves. And in order to modify it, we can change the physics of it in order to encourage different gestures, right? So for example, if I want them to give more attention to the quadratic term, I can make it more flexible. So you have to bend it. And this motion then corresponds to how the quadratic is changing. Or if I want to be able to get a as you say, focus on the linear term, then I can do more of a slope type motion so that people understand the concept of steepness based on how you're gesturing, moving your hands. There's a lot of research that shows that people who gesture more when they're explaining, they actually understand concepts better. And same thing for a shift, right? Like then we should probably be able to allow students to pick up things, make it really stiff, and be able to pick up things so they really understand what a shift means, like embody, right? They can embody those concepts. And so what we did is we made a particle simulation in which we can control the physics of how the particles interact together. And through a very, very simple pincher type haptic device, we can control how those particles feel and encourage students to do different motions based on the concepts that they're learning. And so we're working right now. So we performed the first iteration of the device and we did a first study, and we're working on improving the device based on the results of the study, and also working with students we're going to do summer workshops in order to work with students and try to encourage different gestures and a deeper understanding of these mathematical concepts. And now as we were working on these though, and as we were like bringing attention to polynomials, I had another student then bring attention to another population that's very underserved when they're trying to learn abstract concepts, and that's blind and visually impaired people. We actually interviewed a number of teachers for the blind and visually impaired, and they did tell us like the hardest part for teaching is trying to explain abstract concepts that they learn in the classroom. And so for example, like when you are learning, right, polynomials, right, as we said before, it's not great. The teacher will draw a graph, but then you also have your graphing calculator. And I think if you're curious, and I think most of us were, right, if you want to make further examples of what happens, right, then what you do is you're like, okay, so this doesn't tell me much, but okay, what happens if I now add a constant to it, right? And you're like, oh my God, okay, everything moves up. And so that gives you intuition. It's like, okay, that's what that constant means. It's gonna shift the thing, right? And then you're like, okay, what if I like now do a negative constant? Oh yeah, everything moves up. Okay, that computes, that makes sense. And so, and then other changes are a little bit harder to like intuit, right? Like now multiplying and stuff, but still you can be like, okay, the thing got like larger. Okay, I can jive with that. Or the thing got skinnier. Okay, that makes sense. And even though it's like not perfect, but still like what blind and visually impaired students don't really get the opportunity to do is for themselves to experiment, for them to be kind of the creators and the decision makers, and be like, okay, now I want to see what happens if I do XYZ, right? Usually the way classes for them work is that they're in a classroom, and then they get to work with a TVI a couple times a week, where the TVI will adapt some of the materials for them. And so they'll get, for example, like if you're learning about parabolas, like a 3D printed representation, and then they get to feel a few iterations of that, but they don't really get to be the ones like, oh, what happens if I blah, right? And there are tools, like there are braille displays. Now the problem with these is like really the way these work is like you require one actuator per dot. And even though there's a lot of research and very amazing innovations on like how to create these actuation schemes so that they're cheaper, still is like to have a big display, right? Where you'd be like, oh, I could like render math. Still takes a lot of actuators. It's extremely expensive. And there is still the problem of resolution. Like the braille dots don't have a ton of resolution, so you don't get to do that much. This is an example that a TVI showed us they came up with like this little 3D printed thing, which is great that you get to experiment a little bit, but again, not entirely that much. And so what we did is then with feedback from the TVIs and also working together with a blind partner, we co-designed a mouse for blind and visually impaired individuals. And the way this mouse works is inside of it, it has this little Delta robot. And so what we can do is, again, we program the Delta robot as a haptic device. So what we can do is we sense the position from the user, like how they're moving it, and we can output a force to it, right? And then we conducted studies with blind participants as to what might be the right feeling. Like if I want to render a line, right? Like there's free space and then there's a line so that I can render like illustrations and graphs. What would be the right feeling for that line? And what we came up with is, well, the right feeling for a line should be something like a change in material properties, and also a directional cue. So you can see it here that kind of guides you through the line. So it helps you trace it. And then at the end, like when there's something important about the line or a square or a circle or any other geometric shape, you should have some reference points that are again another feeling, so that users can sense like, oh, okay, this is the end of the line, or this is an important part of that geometric shape. And so as you can see here, the user rests their hand on that button that now is the robot, and then we can control what that robot does, and so what the user feels. And so right now, we've made the first prototype and did studies to understand like what are the right haptic effects and how blind participants can sense this illustration content. And now my student's working with a blind student in a school, trying to see what are the best ways to teach them like geometric and math concepts. Yeah, all right. And I think there was a question. So when
actually, it was a comment.
Oh,
Kontriagin,
it was a comment.
was a
Oh,
blind.
okay.
Yeah.
Yes. Yeah. All right. And so one last project, and then I'll let you go and like ask me questions and whatever you want. So these actually is not entirely like 100% haptics related, but another thing that that really interested in looking at is what is the connection with math and other subjects, and how can we kind of teach math and robotics to folks that maybe would not be interested in math and robotics that much, right? And then we came across this amazing relationship between math and weaving that we're 100% taking advantage of. And so the reason why weaving is so interesting is because weaving is like the oldest art form. There's well, okay, there's also drawing, of course, but in terms of like the complexity of it and the innovations that came because of it, it's just an amazing art form. There's samples of weaving that are as early as 27,000 years ago. And what's really crazy about weaving is that almost any culture that you can think about came up with it seemingly independently, like of course in parts of the world where the land is connected, but you can see examples of weaving and weaving techniques in the Americas and Europe, Asia, almost everywhere, right? Everybody came up with a way to interlace yarns to make cloth. And so, and because of that, also, a lot of different cultures came up with innovations and different very smart machines to be able to make the process more efficiently. And so the thing about weaving is just interlacing two sets of yarn. So you have your warp, which runs horizontally, and your weft, which runs opposite. Your warp, which runs vertically, and your weft, which runs horizontally. And so your warp is the yarn that you set up at the beginning. It's in tension. And then in order to make patterns and to do interlacings, then you interlace the weft. And so you go like over, under, over, under, over, under, over, under, for example, to then interlace it, make a piece of cloth, right? Depending on how you interlace it is the pattern that you will see. So for example, if you go like 1 over 1 under, if you're just going 1 over 1 under, 1 over 1 under, then you're making plain weave. If you instead go like over, under, under, now you're making like basket weave or twill weave, depending on how you shift it around. And so I'm gonna go into the connection with math in just a second, but then what's really cool also is just the innovations that people came up with, right, in order to make this process more efficient. One of those is what we call the shaft loom. And so in the shaft loom, what happens, so basically people did not want to be going over, under, over, under, over, under. Imagine creating like this t-shirt, everything that you own is woven, right? And so it's like, you don't want to be doing that, especially when things start getting finer, right? And so what people came up with is, okay, so let's say that we have these shafts or frames, and every single yarn goes through one of these shafts, right? You can pick which one, but it has to go through one and only one. And then you have these pedals, right? Because I don't want to be reaching over and like lifting those shafts around. You have these pedals. And so then what I can do now is I tie each one of these shafts or a subset of those shafts to a pedal. So I can tie one or more shafts to each pedal. And so now it's just my feet that are doing the lifting, and the process becomes very efficient. And so what happens when I lift up a shaft? Well, then whichever yarns are connected to it lift as well, thus creating like a shed is called, or spacing between the yarns that did not get lift up and the yarns that did. And all I have to do now, instead of having to do that with my weft, I just kind of shoot it through. There's tools for that also. There's shuttles that have little wheels, so you can just like do it quickly. And then once I bring the thing down, it just sandwiches the weft in between the two warps, effectively doing that over under motion, but in just one motion, right? All I had to do was like push, it lifts, I shoot through, I'm done. And so based on these, right? Now, again, here's just another diagram. So I have these heddles that are on the frames. Each warp goes through a heddle, which is connected to a frame, and I have my pedals connected. So just a better visual. And so then when I go to weave, right, what I get in order to know what to do is something called a weaving draft. And so what the weaving draft tells me is, number one, how to set up my weaving machine from the beginning, basically which threads need to go to which shaft, right? So if I'm like in thread number one, like how do I know which shaft to pass it through? Because wherever I pass it through, it's going to lift with all of those that are on the same one. So that's going to affect my pattern at the end, right? So like if I pass, for example, like this number one thread is in shaft number one, then it's always going to move together with every other thread that's in that same shaft. So of course, that's going to limit the amount of patterns that I can do, right? Because threads that are together will move together. And so then I have my tie up, right? Which tells me how to set up my pedals, like which pedals should I connect to which frames. And then I have my treadling matrix, which tells me what I should do at each time step, which pedal should I push. And then I have my drawdown, which is the actual pattern. Well, if we look at these, right, these are all just matrices. Like I can think of my threading matrix as just a number of frames by number of threads matrix, which tells me like, is my thread, like just the binary matrix, is my thread going to be going through the particular frame at this moment or not, right? Then my tie-up, same thing. It's just a frame number by pedal number matrix that tells me which it's going to be, again, a binary matrix, whether that specific frame is going to be connected to that specific pedal. And that's it. And same thing for my treadling. Again, another very binary matrix, which just tells me what I'm going to do at each time step. So at each time step, which pedal like should I push? It can, it can be more than one. It doesn't matter. It's more ideal if it's just one, because it's easier on me and my body than having to think about like pushing with both feet and stuff. But it doesn't really matter. And then my drawdown at the end, again, another binary matrix that just tells me which one of the threads am I going to be looking at that moment. So if the threads that were lifted, right, those threads that were lifted, well, they're going to be on top of the one that I passed through, right? And the ones that were not lifted, well, then the thread that I passed through, that's going to be on top, right? And so it tells me like which one I'm looking at, and that's what my pattern is going to represent. So in the end, the way I can decompose designing patterns for weaving is just as a matrix multiplication. And so of those three matrices, because those three matrices entirely are going to determine what my actual pattern, what my drawdown looks like. And so now that we have that representation, we can pose in mathematical optimization problems based on it, right? And we can teach weavers and artists how to do it themselves. Like we can tell them, for example, like, oh, like if I want my treadling to be this, and my threading to be this, and my pattern to be this, what should my tie-up be? Because these are binary matrices, the operations are actually quite simple. You can almost solve this by inspection. So it's a very good way to teach folks that normally would be like, oh, I'm not really that good at math, or, just to do it, because you can kind of just do it by inspection. And so now that we have this representation, right? Number one, it's just like, it gives us a way to analyze these patterns, which I'm going to explain, opens up a ton new performance analysis. And it also empowers these artists to now do their own, do their own pattern creation and their own weaving drafts. Like if you buy a weaving draft software online, it costs thousands of dollars a subscription a year. But you can do the same thing if you understand it's just on an Excel spreadsheet. Like you don't need to pay thousands of dollars, right? And there's a lot of other analyses and very interesting problems that come out. Like for example, like if I'm beginning to set up my pattern and I want to be able to to know, oh, can I actually weave these? Like I designed these and I drew it and I think it's beautiful. Can I actually weave it using my loom? Well, that actually depends on the rank of the matrix that my pattern represents. Like the rank of the matrix is going to determine how many shafts, it's going to determine how many actually independent columns I'm going to need in order to be able to weave these. So if my rank here, if it's a 4-rank matrix and I only have 2 shafts to work with, well, then I'm going to have to change my pattern in order to actually be able to weave it, right? And so now I can create my own weaving drafts. There's a ton other things that I can actually do. There's ones that I have decomposed these weaving into mathematical operations. There's a lot of other very interesting things that happen in weaving. One of it's double weave. So there are times when you want to be weaving 2 cloths at the same time, 2 or n, right? If you have like an infinite shaft loom, you can weave n different cloths at the same time, right? And the way if you're weaving like 1 cloth versus 2 cloths is using set theory. You can see like which threads will never pass under which other threads, right? And that's also an analysis you can do beforehand. So when you have a pattern, you design the most beautiful pattern. Well, you can analyze it in order to understand, like, is this going to weave as 1 cloth or am I actually making a mistake? Or am I intending to weave 2 cloths? And that's also perfectly fair because sometimes you want to weave pockets, right? Or pillows or, whatever you want. And with that, there's a ton more. Like you can analyze the quality of your cloth also by the number of, by using vector calculus, actually. There's a ton more. And I don't know why, but like around the 80s and 90s, mathematicians went crazy in the best possible way with just analyzing weaving through math. So if you look for papers online, there's a ton of other examples and things that we can teach students about just understanding their cloth better and their weaving better through doing math. And then the other awesome relationship between like weaving and the world we live in today is that the first computer was a weaving machine. Of course we saw shaft looms, right? But there are limitations to them. Like beforehand, you have to make the decision of like, how am I gonna thread it? Rethreading it is a pain in the butt. Like it takes like 2 days. It's not even funny. Like that's the part that I hate about weaving. And so you have to be like, okay, once you're stuck with a specific thread and you can change your tie up, but there's a limitation to the patterns that you can make. And so people did not want those limitations and they wanted to be able to actuate each thread independently. And so to actuate each thread independently, they made this amazing thing called a jacquard loom. And it's actually so each thread is on its own little actuator. And the way it automatically works is actually punch cards. Punch cards decide which threads are going to be, actuated at each time step. And that was the first computer. That was the first use of punch cards. And from there, of course, there's other innovations that came to give us the computers as we know them today. But it is very interesting that the first, computer machine came from us wanting to dress ourselves. And so what we did is we made our own version of a jacquard loom. It's a little robot that's a kit. And so it only has 40 threads, which is still, still plenty. But so 40 threads it can support, and students build it themselves. And so they build it and then they use it to weave. And then what we do with these is we teach a class where so an undergraduate kind of like introduction to robotics class where we combine concepts in vector math, in robotics as they're like weaving their looms. We also teach them how the electronics work that support it, mechanical, what mechanical design decisions have to come into it, and also weaving, the history of looms. So we have that CMU undergraduate class. And we've seen very positive results with students. We get students from all over, from the art school, from architecture, from robotics, from CS, coming together and making their project. All right, so I know I talked a lot. A summary. Okay, so in summary of this talk, haptics is awesome, but very complicated. We do need novel haptic actuation technology. Math is hard, and tangible math, learning through haptics and robotics could really help. Yeah, and I just want to thank like this, of course, the work of my amazing students, not my work, and my sponsors. And I will take any questions that you have.
Thank you so much, Melisa, for the great talk. And Joel has to left early for a faculty meeting, and he asked me to say sorry for him. Yeah, this talk is so great, and it's just awesome to see the tactile technologies can have so many different applications in like to help different people in the society. And there is a question in the chat, and I can read it. So this is a really cool approach to use haptics. How is haptic feedback measured both for known objects such as custard and unknown objects such as tocine? Are measurements qualitative or quantitative? Are there standards for specific feedback?
That is a really good question. Yeah, one of the biggest issues with haptics is that, especially when you come up with a new device, right, is that the measure of how, like, what the thing should feel like, a lot of it depends on human perception, which is very biased and subjective, right? And so in haptics, what we do a lot is we use something called psychophysical experiments, in which for a specific device, we do experiments to try to understand how humans are perceiving things with that specific device. And so if you're rendering something physical that exists, right, like the custard, right, you can actually measure the stiffness of the custard, right? You can grab an instrument machine, you can measure that, and then you can try and render exactly the same forces. However, a lot of the time, especially when we're rendering something extremely stiff, because the motors that we use to render haptics, we also want to be able to render free space. They don't have gears, and so they're not very high torque output motors. And so rendering something extremely stiff is very rare. So that's also why we use the visuals to kind of trick the user. So when you use visuals, you're now kind of bringing the sense of vision into it too, and to kind of trick the user so things feel more like what you want them to feel, right? And then so the short answer is there's not like a golden standard for if I want to render XYZ, this is exactly what I need to do, because we don't really understand what that should be. And because we also understand the limitations of our devices, you're absolutely not going to be able to render infinite forces. Like if I want to render a super stiff wall, you're not going to be able to render that with the same device that you would be able to render something super soft. There are devices out there that just render like, they'll just be like a clutch where they just stop you, right? And then in that case, you can render that binary like super stiff, not super stiff, but you won't be able to maybe render so many things in between. So the psychophysical experience, what they get us basically is just understanding the capabilities of our device. And then what we do with that is how can I trick the user into feeling different things because my device is just not capable of doing it. And yeah, and then so that's for real things. In terms of abstract things, yeah, it's all up to you. Like again, what we do to try to measure that our devices are effective is we do psychophysical experiments where we prove, for example, like what is the resolution of my device? Like how many different feelings of this kind can I actually render so that I can be effective, and I can actually say like, okay, so if my sine wave is changing by a factor of 2, can I change my feedback by a factor of 2 as well, right? But yeah, it's all very subjective still, because we can't do everything. But thank you for the great question. I hope this helped answer it a little bit. I'm sorry.
Thank you for the answer. Any other questions? Okay, no questions. So yeah, thank you for the great talk. And I can imagine that, like, if, for example, if Controlierian can have this kind of technology to help him to do research, he can have like more like great discoveries about control method. Yeah. So yeah,
Yeah.
it's so nice to see technology can benefit human beings and our community and society. Yeah. Thank you so much. Thank you again.
Thank you. I really appreciate the invitation. Thank you so much, everybody.
See you. See you.